Good morning, everyone. We come to lecture 19. So in this lecture, we'll talk about the Aharonov Bohm effect. Aharonov Bohm effect. And this effect is related to Berry phase. So we'll first talk about what this effect is, and then we'll learn how this effect is actually an example of Berry phase, an example of Berry phase. So this effect is predicted in 1959 by these two people. I think they discovered them independently. So it was named after both of them. So it is pronounced as, I mean, for a long time I didn't know how to pronounce it properly until this morning. Okay, I check it. It's pronounced as Aha. This is Aharonov Bohm effect. Aharonov Bohm effect. Okay. So let's consider what this effect is. So let me show you the experiment. Okay. These two predicted it, and it was later confirmed by experiment. So what the experiment is like? So first you have a solenoid. Okay, you have a solenoid. So inside the solenoid, there's some B field. Okay, constant B field is just B field. So uniform B field inside. Uniform B field inside. And then B equal to 0 outside. I mean, this is the property of an infinitely long solenoid. Okay, inside the solenoid, the B field is uniform. Outside the solenoid, the B field is 0. So now, let's consider a particle beam. Okay, like you have a beam of particle. For example, an electron beam. Okay, you just imagine just an electron beam. It can be a single electron because it is described by a wave function. So what we're going to do is a single particle theory. So you just imagine there's one electron, and it is a wave function, a wave coming in, and then this this electron is split into two beams. Okay, one go behind the solenoid, the other go before it. Okay, go like this, and then recombine. So this is the input intensity, and you split it into two beams. Each of them has 1/2 of the intensity. Okay. Then you measure the output. So this B field can be this B field will be proportional to the current of the solenoid, to the current. And then if you use the classical picture, there's no B field outside. Okay, there's no B field outside. The particle does not see any B field. So you would say there's no difference between this beam and this beam because both of them see identical 0 B field. There should not be any difference between these two beams. So if you use the classical picture, so let me just plot it out. So you plot I out as a function of B field. But pay attention, this B field is the B field inside the solenoid. Or you can say, or you can plot it as a current. It doesn't matter. Okay. So it's inside. So for classical picture, you will expect it's constant. You will expect expected results of classical picture. There should not be any difference because the B field is inside the solenoid, not outside. Outside there's 0 B field. So you change the B field outside the range of the particle, then it should not change anything. Okay, so you expect there's a constant value. But the experimental outcome is not like that. The experimental outcome is something like this. The experimental outcome turned out to be oscillating. If you change the B field inside the solenoid, you actually have an effect outside your solenoid. And it turned out that there will be interference between these two beams. So this one will pick up a phase, and this one will pick up another phase. And it turned out that they will actually, this one will be interference. Will be interference. Okay, and then once you have the interference, then you have oscillation. This two phase turn out to depend on B. Okay, this will turn out to depend on B. So now the surprising result is this. The surprising result is this. The B field. I should use one inside. Inside the solenoid. Solenoid can affect the particle outside the solenoid. Okay, so this is the surprising effect. Okay, so how do we explain this phenomenon? It turned out that the potential plays an important role here. Okay, plays an important role. Okay, so let's review a little bit about classical E&M. In classical E&M, electric field can be expressed as the derivative of the potential. Okay, so and if you have a change, this potential, this potential are not measurable and not unique. Are not unique. So you are not supposed to have any effects that is directly related to this. You only E and B are measurable. Okay, only E and B are measurable. So you can actually have a certain gauge transformation. If you use a gauge transformation, okay, if you go to a gauge, if you use a gauge transformation, this go to minus lambda, and then A go to A plus then you get the same E and B. So here, this eta xt is an arbitrary function. It's an arbitrary, a smooth function. I mean, it needs to be smooth so that it is differentiable. Okay, so now let's consider the Schrodinger equation. You find that the Schrodinger equation does not depend on B and E directly. For Schrodinger equation, Schrodinger equation, the Hamiltonian equal to 1 over 2m h over I and QV. So H depends on A. I mean, here you use this then. I mean, you can use this then. Okay. I mean, so some textbook use V, some textbook use this. Up to you. Okay. Not. So you see that in classical mechanics, the Maxwell equation depends on E, depend on B. The Lorentz force law depend on B. Those are all measurable quantities. So in classical mechanics, this kind of expression is just mainly a mathematical convenience, just to make the mathematics easier to deal with. But when you really do the calculation, the result only depends on E and B. However, once you go to quantum mechanics, you find that the Hamiltonian has no direct dependence on E and B. It actually depends on the potential. Okay. So this will give you some non-trivial consequence. So first, let's consider something directly related. Okay, you have a gauge transformation. So if you do a gauge transformation on the Schrodinger equation, what will happen? Okay. So if you okay, if you if we transform this, you can actually deal with this by yourself, okay, as an exercise. Here I just write you the answer. So the wave function will become so the original wave function is like this, x and t, okay. Then this one will become times e I lambda. So that means if you apply any gauge transformation, eventually the wave function is going to gain a phase, and this phase has local dependence. Okay, it can be any smooth function here. Okay, of course, when you deal with those expectation value, all those things, this one will just cancel each other. Okay, so you won't have any like a non-trivial result. Okay. However, if we apply this to this case, then you'll find some non-trivial result. So let's apply it here. So first, we need to consider the potential in this case. So in this case, on the top view, let me deal with on top view. On the top view is this. You have a solenoid. Okay, let's say the solenoid has some current. Okay, has some current. Okay, this current going. Then the B field will be, the B field will go out. Okay, the B field is constant. Okay, this is inside the solenoid. So outside the solenoid, the B field will be 0. Okay. Let's say this radius is I is 8. Okay. Let's say this radius is 8. Okay. So now let's consider at any point R, let's say, let me to make this like this. This is A. And then let's consider an arbitrary point R. Okay. So what is the A like? The A will be pointing in this let me I need to define the coordinate first. Okay, this is X. Okay, let me define this as R. This angle is 5. Okay, so this is R. So the A will be equal to A R. This will be the form of A. This will be the form of A. Because the B goes out. So and the B is the curl of A. So the A need to the A will be circularly symmetric. The A. Let me draw it. The A need to be something like is it symmetric? Okay, something like that. Okay, so this will be the A. This will be the A. So the A will have this like this. Okay, it will go on the tangential direction. Okay, so let's get the form of A first. Let's get the form of 8. So here B equal to curl of A. So we're going to get the form of A for this particular problem. So first, let's do integration A dot dl, the curl, okay, equal to, use the Stokes theorem, and then dA is the area, and then this is just B dot dA, and then this is the B times area. And then this is, I call it this, the flux, magnetic flux. Okay, so this A, due to symmetry, this A will only depend on R. It won't depend on the angle because it's the whole thing has a cylindrical symmetry. So we know that the form of A will have this form. So what we need to get is the expression of AR. Okay, so for this one, this will be AR times 2 pi R. Okay, so that this total length is 2 pi R. Okay, and then this one will equal to the flux, will be equal to the flux. Okay, so now let's consider different cases. Let's consider different cases. If R is smaller than A, that means you are inside this solenoid. Okay, this is the solenoid. Inside the solenoid. If you're inside the solenoid, then the area would depend on the R. Okay, the area will be pi R squared. Okay, so AR 2 pi will be equal to B times pi R squared. Okay, so AR will be B pi R squared 2 pi R. So it will be BR over 2. Okay, this is 1. Okay, in the second case, if R is larger than A, then the area with B field is fixed. Is pi A squared. Because it's outside. Then this AR 2 pi R will equal to pi A squared. Okay, then the AR will be then it will be BA squared over 2R. It will be proportional to 1 over R. Okay, so this is proportional to R. So if you plot it out, if you plot the A, if you plot the AR as a function of R, it will increase. So this is A. It will first this it will first increase like this, increase to here. And then it will drop like this. It will drop. Do it smoothly. Okay, so this will be proportional to R. This will be proportional to 1 over R. Okay, so this is the form of the magnetic potential. Is that okay? So the key thing here is that even in the region with B equal to 0, AI is not 0. Okay, so this region is B equal to constant, and this region is B equal to 0. Okay, so you can see that the key feature here is that even in the region where the magnetic field is 0, the magnetic potential is not 0. Okay, so this will have some non-trivial effect on the Schrodinger equation. Okay, on the Schrodinger equation. Okay, so now let's consider. Okay, let's consider an electron confined in a circular loop with the radius B. Okay, so let's go back to this copy, the solenoid. Okay, so this is solenoid. So now let's say this is B. Okay, I just okay. So now this A here will be this thing. Okay, then it will be let me see, will be BA square, BA, and then 2B. So you just use this equation. Okay, you just take the R to be B, that BA square over 2B, and then you add the vector. So that will be the vector potential in this loop. Okay, so now let's consider there's an electron here. Okay, the electron is confined in this loop. So the electron is free to move in this loop, but only in this loop. Okay, we want to see how the electron energy will change due to the magnetic field inside this. Okay, so so now let's write down the Schrodinger equation. The Schrodinger equation will have this 2 mass HI and then QA. Okay. So this will be Q. So this one will be 0. Okay, will be 0 because here we don't consider any electric field. So it's only this part. You can expand it. You can expand it. So after you expand it, you get something like this. Q square and then 2I H bar QA dot. Okay, so here we make use of the fact that this one dot A is 0. You can easily deal with this. With this form, this will be 0. This will be 0. Okay, so you just open this parenthesis, use this thing, and then use some calculus relationship. You'll be able to get the form like this. There's no approximation. You just open the parenthesis. Okay, so now then let's deal with this part. Okay, so this A here, we're going to set it as, we're going to use this relationship. So for simplicity, we just add the pi back. We just add the pi back here. So this will be the flux. The flux. And later we'll show you that the result depends on the flux. So we just use the flux in this way. Okay, so now let's consider this term. Let's consider this term. Dot. We're going to use this relationship. This one in the circular coordinate, it has a form like this. Okay, it has a form. Okay. So this one, of course, in this case, will become 1 over B because in the loop. Okay, because the radius is 1 over B is B. Okay, so then you just take this and then take this. And then you just dot. Okay, you just dot. And of course, eventually the result will be simple. The result will be you just open the parenthesis and then the dot product is only on the vector. Okay, so it's only on the vector. So this one will equal to 1. Then eventually you get something quite simple. And then, okay, so this is this. So now let's rewrite the Schrodinger equation. Okay. Okay, so the Schrodinger equation. So H will become, so we're going to write all this out. Let me see. Two M negative. And this will be all become okay. So yeah, because you have this, okay. So if you have this square, this will become B squared. Okay, so you put it in here. Then plus Q square. Then your A will be this one. Okay, of course you have a square plus 2IHQ. Then you put this in. Okay, so we can actually write out the whole equation. Okay, so let's write it out. The wave function. Let me use this wave function. Equal to E. Okay. So that means this one equal to E. And then okay, so now we're going to simplify it. Now we're going to simplify it. So first, we're going to times this thing for on all of them. Okay, let me rewrite it. No, times multiply on both sides. And then this will be, then you have Q squared. Not multiply, just multiply this. Q squared. And then this thing is going to square. This will become 4 pi square B. Okay, this is this part. And then 2mb square. And then 2IHQ. And then same. Yeah, sorry, the algebra is a bit tedious, but okay, so we're going to simplify one by one. For this term, then this will become 2. This will cancel, this will cancel. So eventually you get something equal to negative Q and then H yeah, I think this mass, I make a mistake. This mass is everywhere. This mass is everywhere. I forgot to times it. Sorry. Let me put the mass here. 2m here. Okay. So sorry, it's a bit messy. Then you don't need the 2m anymore. You don't need the 2m. Okay. On both sides. Then there's no 2 mass. Okay, I make a mistake. Okay, no 2 mass. The 4 is still there. Okay, so this will be 2 pi h bar squared. Okay, and then this one, let's see. Then you just cancel this, cancel this, cancel this, cancel this, and then this I, this will become negative I. The 2 is cancelled. IQ and then pi h bar. And then you can add the 2 here. And then 2 pi h bar. We're going to define beta equal to Q. Okay, so sorry for all this thing. So eventually, after you simplify everything, so you're gonna have this 2I beta and then D and then plus epsilon and then equal to 0. So this epsilon is what? Let me see. Let's add one more step then. Let's add one more step. 2I this. And this is also beta. This is also beta. So this will be negative beta square. And then this thing equal to this thing. Okay, so we're going to do one more step. This thing go to here. Become positive. Okay. So okay, then this is equal to 0. Okay. So we're going to define this. Define it as epsilon. Define. I think that is all still partial differential. Second. Partial. Okay. Doesn't matter, right? Okay. Define it as epsilon. Okay, so eventually you get this result. Epsilon. Okay, so this equation is actually exactly solvable. Okay, this equation is exactly solvable. So the solution has the form equal to A I lambda. I mean, you can use this form and get the lambda. Can be solved. can be okay, so let's get the lambda. Okay, we'll get the form of lambda. So since you have this derivative, then let's just do it one by one then. Okay, if you do it one derivative, then you just a I lambda. You do it one more time. They do it just twice. Yeah. Okay, then you just plug it in. Put them into the equation. We get, so basically for this one, this you get, for this one you get this, and then minus 2I lambda, and then you get this. Copy, and then plus, then you get this. Equal to 0. Oh, this A has nothing to do with the magnetic potential. It's just a constant. Okay, so here, then you can already start to cancel the A. Cancel this A. Okay, cancel this. Then you'll get another simpler equation. Then just erase this. Okay, so what you get is something like this. Did I make a mistake? Oh, I make a mistake. It's this one. I had to make a wrong copy. This is the copy. This is the one. Okay. So this is. Okay, so you get the quadratic equation. So let's write it out. You open the 2I and negative 1. So you have plus 2 lambda, 2 beta lambda plus. So this is just a quadratic equation. So we get the solution immediately. So this lambda will be equal to this. This will be negative 2 beta plus and minus. This will be 4 beta square plus, minus, this will be 4AC minus this. Okay, then this will be negative 2. You solve a quadratic equation, and then you cancel it. This negative one, after you go into here, is still plus and minus. Okay. Then the 2 go into the square root, will cancel the 4 here. And then, yeah, so eventually you get this. You get this. Okay, so let's recall the definition. Okay, let's record this. Record this definition. This is beta. beta. And then what is epsilon is this thing. Okay. Okay. Putting in and epsilon. Then you'll have lambda equal to, I just copy them. Copy plus minus okay, it turned out that this two can be canceled. Okay, these two can be canceled. And then you get this. Plus and minus. The B and H bar can come out. Then you have 2ME. Okay, so that is the solution. Okay, now you need to know that this is a solution for a loop. Okay. It's a state wave function in a circular loop. So that means if you have 2 pi, basically you just say 2 pi. If you use 2 pi, need to be 0. Because it's a loop, right? You go back to yourself. So what does it mean? That means A, EI, 2 pi need to be the same as A 0. Okay, so that means lambda need to be an integer. Okay, it can be n 0 plus minus 1 plus minus 2 dot dot dot. Okay, so this is the condition. This is the condition for circular loop. So that means this must be an integer. Okay, so that means this. So that means lambda equal to this equal to n, and n is an integer. Okay, so we just reverse it. You reverse it, then you get the energy will be equal to I just write out the result then. Okay, will be h. I mean, you reverse this, you get this answer. Will be plus e 2h h bar square. I mean, it should be negative q. Okay. I mean, if you take if we take q equal to negative e, then e will just become plus e. This plus or minus let me see, plus minus. It doesn't matter actually, because after this go to the other side, you make a square, then the plus minus just go away. Plus minus go away. Okay, so this is the result. So let's see the physical significance of the result. Okay, so at At B equal to 0, that means that the flux is 0. The flux is 0. Then E, this will be 0. So E just H. So there's a twofold degeneracy. For n equal to +1 +2. So the positive and negative number, they get the same degeneracy. But when B not equal to 0, this is not equal to 0. This twofold degeneracy is lifted. I mean, you can easily see that this degeneracy should be related to a time reversal symmetry. That means the particle going this way and going the other way, they are the same. They are the same. However, once you apply B field, then this tool, like this tool, let's say this is the loop. This tool. Okay, if the particle going this way, let's say I don't know how to draw it well. Okay, if the particle going this way, or they're going to another way, they're not going to be the same. Okay, so if you go to opposite way, they're not the same energy. Actually, the wavelength might be different. I should not just directly copy. Okay, because the energy is not the same, so the wavelength might be actually different. Okay, so this is already a significant result. Why? Why is it significant? You look at here. In this case, the B field are all inside. If it is a classical particle, the particle doesn't see the B field inside. It's just moving outside. Like you will not know what is happening inside. You're just moving outside. You should not feel anything at all because you don't see the field inside. But when you solve the Schrodinger equation, you'll find that this particle going this way or going this way, they're going to have different energy. So how can an area without B field will affect the energy of a particle? How is it possible? Suppose this one is completely concealed. You actually have, you don't know what is inside. There's no communication. I mean, I should not say no communication, but at least for any measurable quantity of the B field, this particle doesn't feel the B field. So for classical mechanics, you go this way, or you go this way, there should not be any difference. But when you solve the Schrodinger equation, you actually have a measurable difference. That is, the degeneracy is lifted. At the gap, the gap between the two non-degenerate states is going to depend on the B field inside. Okay, so this is a significant result. This is a significant result. That means, basically, it means the whole theory is kind of a non-local. Like you change one thing in one place, you're going to affect it on another place. Another view is that this magnetic potential has a measurable consequence on the world. Okay. In classical mechanics, if you have a zero B field, you're not going to have any effect. But in quantum mechanics, actually, this finite potential here, the potential is finite, actually will have a consequence on the outcome. Okay, it is actually very mysterious. Like this potential is not anything that is measurable. But when it is non-zero outside the range, when the B field is zero, it will have a consequence on the outcome. Okay, so that is the mysterious part about quantum mechanics. Okay, in classical mechanics you don't have this result, but in quantum mechanics you have. Okay, now let's consider a general case. Let's consider a general case. I want to make connection to the Berry phase. Okay, so let's consider a general case. Let's consider a general case. Okay, when you have a Schrodinger equation 2m plus here I use a v, then I just follow the textbook. Okay, I just use a v. The v is a function. Okay, so now you have a function. So how do we deal with this equation for a general v and a general a? Okay, how do we deal with it? So for the region, that b is zero, you can define another way. You can define another function. Let me call it this phi prime, such that this one equal to this prime times a EIG. Okay, what is G? And G equal to Q over H bar from an arbitrary point R. Okay, the arbitrary point R. Okay, to R. So this R is an arbitrary point. Arbitrary point. Okay, so G is well defined if this equal to zero. Okay, why? If this is equal to zero, then basically any of this loop equal to zero. Okay, because this equal to the area. Equal to zero. So this integration does not depend on the path. Is that okay? So this is the integration from R. You just integrate to R. Okay, if this whole area be equal to zero, then it doesn't matter what path you take. Like you take this path, you take this path. Okay, so all paths give the same integration result. So we can dot. Okay. So in this region, we can use this transformation. Okay, so this kind of expression is only good in the region when the B field is 0. And this is exactly what we are dealing with. We're dealing with the region, the B is 0. So we can use this kind of expression. And this is going to be simplified. This is going to simplify the Schrodinger equation significantly. Okay. So we're going to plug this into the Schrodinger equation and see how we will simplify it. Okay, so let's going to deal with this. Okay, we're going to deal with this. So let's first consider the derivative. Okay, so since we're going to plug it in, so we're going to this is going to be the gradient. Okay, gradient. Okay, so you're going to have a gradient of this one. And then plus a gradient of this one. Okay, what is this? This will be just the gradient of G, I, and then E, I, G. I just use the chain rule. And what is this? This is just the gradient. You just use the definition. Okay, so once you use the gradient, then you'll get, by the way, there's always a vector here. Then you will get A, and you get this. Okay, so eventually you're going to get this thing plus what? Plus IQ H bar, and then A, and then this prime, and then EIG. Okay, so what is this? This is just equal to the original function. Original function. So okay, so you have this and this. So you just use this. I use this thing. You use this thing minus this thing. We're going to minus this thing. Right. Then it's going to equal to this. Okay, so you can kind of simplify it. Okay. So this is already one part of the Schrodinger equation. Okay, because the Schrodinger equation has this part, right? So we're already dealing the first part. But now we're going to deal with the square here. We're going to deal with the square here. So how do we deal with the square? Then all you need to do is to apply this twice. Apply this twice. You just apply it on one side, and then also apply it on the other side. Okay. So then let's copy. Then this will become square. This will become square. Okay, so we're going to deal with this side. We're going to deal with this side. Then we have there's some math we have to go through. Okay. Oh wait, did I miss something? Uh, I sorry, let me this one I'm missing something. Sorry. I actually should, it doesn't correspond to it yet. You times h over I, then here, and minus q. Then here you put it here. Then here you times h bar over I. Okay, so that is the one that we should deal with, because this one will correspond to here. Okay. Yeah, to this form. Okay, sorry. A small mistake on my side. So let me do it again. Okay, this one will be faster. Okay, so you have a square here, and then okay, so we're getting there. So we're going to separate it. We're going to separate it. The first one will be this term will times this term, so it will become negative h bar. And then, wow. Okay, then minus q h bar over I. Okay, so we're going to get this one. This one will be E. You have this E squared. Okay, so this one we already calculated before. This one should be a dot. Should be a dot. This one we already got it before. Okay. U h bar, and then A E I G. This is a square. Okay, so eventually you will have what? You will have this term. This term is negative h bar. And then EIG. And then minus this term, minus this will be negative I H bar U A dot. Okay, then sorry, I'm missing one part here. I'm missing, there's an A here. I'm missing this. There's an A. There's an A here. Okay, so this one will be plus I QH bar A okay. Okay, so now it turned out that these two will actually cancel each other. Okay, so that is the great simplification. Okay, it just magically happened on this step that these two terms cancel each other. So you only have one term. Okay, so this greatly simplified the Schrodinger equation. Okay, this greatly simplified the Schrodinger equation. So now let's go back to the Schrodinger equation. Let's go back to the Schrodinger equation. Okay, so the equation is simplified into this part. You know, this one is, I mean, you can separate it. You can separate it into this part, and you can separate this. You can separate it. So now this becomes this. Okay, so we already got this. Okay, we got this. Then we just write it out. You have 2m, and then this. Negative. And then plus. This one, you can also write it out as okay, you need to know G has no dependence, on time. Okay, so that means all of this this is just a multiplication. So that means you can actually group this together. The G go out. Okay, the good thing is that now this one get canceled. The whole G is removed. So you get a simplified Schrodinger equation. Wait, did I make a mistake? Sorry, I think there's no 2m here. There's no 2m. This 2m is only on this part. Yeah. This 2m is only on this part. I just keep making mistakes. Okay, so eventually you get a Schrodinger equation for this psi prime, for this psi prime. And in this equation, the good thing is that there's no magnetic potential anymore. There's no in this equation. Is that okay? So that means if you solve the Schrodinger equation in a region without the magnetic field, all you need to do is to solve a Schrodinger equation with no magnetic potential. Okay. So okay. So if the particle is in a region with B equal to 0, then solve the Schrodinger equation. With A equal to 0 first to obtain then the final solution will be this will be this times G. Okay, so now you separate the magnetic dependence into two parts. This one, no dependence on A. This one has dependence on A. Okay, so basically that is a kind of a technique to solve the Schrodinger equation on a region without magnetic field, but with A. Okay, without B field, but with A. So the way to do it is to use the property that curl of A is 0. You can define the G. Then you solve the Schrodinger equation without the A, and get this psi prime. And then you times this phase factor. Then that is the solution. Okay, and this solution, this technique only works on the region with no magnetic field. Okay, only works in the region with no magnetic field, because this one is only well defined when magnetic field is 0. And this is what our case is about. This is what our case is about. Okay, so now let's see how this will help us to make the connection to the Berry phase. Okay, let's see how this will make a connection to the Berry phase. Okay, so now let's consider the solenoid. Okay, you have a solenoid here. Let me go back to the beginning. I copy this. Okay, so let's consider. Do you remember what the Berry phase is? I mean, we learned this last time. A Berry phase, when you have a Hamiltonian that depends on a certain parameter, and then you move slowly in the parameter space and go back to itself, then you pick up a phase. That is the Berry phase, right? So we need to construct such a situation that the particle go around and go back to itself, and it will pick up a phase. So the way we do it is we're going to consider this. Okay, so let's consider a small box inside. Let's consider a small box. I mean, it can be big, it can be small, it doesn't matter. Okay. Let's consider a small box. Okay. So you take the center of the box as R. You take the center of the box as R. Okay, so now you're going to, and then this will be, and this will be, and this will be R. Okay, and then this one will be R minus big R. Okay, R minus big R. Okay, and then you consider this box, the particle is going to confine within this box. Okay, you just build an artificial box. The particle confine inside the box. Okay, inside the box. And the potential is, you can approximate it as the potential with the potential V equal to R minus R with the confining potential. Okay. Confinement potential. So you build a box with this confinement potential, and then just trap the particle inside this box. Okay, so what is the Hamiltonian for this particle? The Hamiltonian for this particle will be this one. Minus Q A R square plus V minus R. Equal to E. Equal to E. Okay, so here, this Hamiltonian will depend on R. Okay, so now you have a particle confined in a box. The box has the coordinate of big R, and then this Hamiltonian would depend on the position of this box. Okay, if this R changes, your Hamiltonian is going to change. Okay, then we are going to use what we learned in the last lecture. In the last lecture, you say if you have a Hamiltonian depend on a certain parameter, then you let that parameter to change slowly, and then go back to the initial position. Okay. So so we're going to let this N R be the eigenstate of this. With energy E N R. So N is the quantum number for the eigenstate, and big R is the parameter of the Hamiltonian, and the corresponding eigenenergy is ZR. Okay, so suppose suppose this box is sufficiently small, then all those energy levels will be discrete. You remember what we learned in the adiabatic approximation, right? Is you have some discrete level. If you change the Hamiltonian slowly and there's no degeneracy, they're going to. So in this box, you're going to have E1, E2, E3. Then once you go into a different R, okay, once you go into a different R, I should use a different color. Okay, if you go to a different R, I mean, this should be horizontal. Then you are going to have, you're going to have E3R, E2R, E1R. So they evolve smoothly. So according to the adiabatic approximation, they will move smoothly, and all of this will be the corresponding eigenstate. Okay, so then let's make this thing. Okay, so let's make this thing go one round. Okay, so now we're going to make it. We're going to cause this to go one round. Okay, so make the box move one lap. Okay, you just move this box one lap. So your Hamiltonian is going to make one lap. Is that okay? Your Hamiltonian is going to make one lap. Go back to itself. So according to what we learned, you pick up a Berry phase, right? You still remember? Okay, so what is the form of the Berry phase? So let's recall what we learned. Okay, if go one lap, the wave function will pick up a Berry phase. And the Berry phase is gamma, okay? And it has the expression, it has the expression of this. Go one lap, and then this n, and then you have derivative r and the dr. Okay, dr. And you can use the curl. Okay, you can use the curl, and then this will become area. So this is what we learned last time. Okay, now we're going to plug in into this equation. Okay, so we know. Okay, we know that here this thing is now this n EIG. Okay, how do we get this form? How do we get this form? Because this equation, when you solve it only inside the box, okay, when you solve, okay, let me get this. Okay, okay, if you solve it inside the box, so this one will become the solution. The solution will have this form. Of course, this one will become this. This one will become, this will be 0 because inside the box, it is 0. Okay, inside the box is 0. So this will be prime. This will be prime. Sorry, this will be I. Okay. Eventually, okay. So you just set this to be to be a smaller one, then EI TH bar. Okay, you set it to be like this. Then this one, this original one, will be this phase. Pick it up. Pick it up. Okay, so basically you have a box here. You solve the eigenfunction within this box, and you know that the eigenfunction is going to have this form. It's going to have this form. This is the one, the solution when you have no A. And this is the phase factor you add. You add it there because there's an A there. Is it okay? Is it okay? Okay, so this is the wave function. We're going to plug it inside. We're going to plug it inside. So the real wave function will be, I mean, this is what we learned before, right? Prime with IG. Okay. So of course this one will be E. And this one will be E prime. And then the energy are the same because in both cases the energy are the I think they're the same, right? Okay, yeah, I think they're the same because once you do the derivative, it doesn't depend on that. Okay, so eventually you get this form. Eventually you get this form. You get this form. Okay, so now we're almost done. We're almost done. We just need to plug it in. Okay, so we're going to deal with this. Okay, we're going to deal with this. Let's deal with this first. Copy. Okay, so let's deal with this first. So we're going to copy. Okay, we're going to deal with this. Then we're going to separate it. Plus okay, so let me see. So this one, what is this? So now we recall G equal to this. We recall that G equal to Q H R. So this is an arbitrary point. Okay, so if you deal with dr G, so you're going to deal with this QR. Now, this one is an arbitrary point. So when we first define this, it's an arbitrary point. It's an arbitrary point. We set it to be R here. Okay. I mean, this can be an arbitrary point that you pick. So we just set it as R. So when you do the derivative R, then you're going to make it become, this will become negative, will become negative dr. Okay, you make it become negative dr. So because this is R, this is R, and this is a big R. So doing derivative on the big R will be the negative derivative of this small r. Okay? So once you deal with this, then you're going to pick up a negative sign. You're going to pick up a negative sign. So this one, deal with this will be A. So you have Q, H, and then uh, AR. You're going to have AR. Let me see. DR. You're going to have AR. Okay. And since we're making a box small, okay, so the value will be just near R. Okay, will be just near R. Okay, so we're done with the first part. We're done with the first part. We're done with the first part. And then we're going to deal with the second part. We're going to take this one. Okay, so let me take this copy. Like this. So this one will be this, right? So you copy this. And then you're going to make a derivative, a complex conjugate. And then you're going to take this one. Let me see. This one will become negative QH A AR. Okay, so we're going a little bit slow, but we're almost done. Okay, we're gonna take this. And then also take this. Minus. And then you're gonna do the integration. You're gonna do the integration. Dr. Let me see how we're gonna deal with it. So this is the first part. This is the second part. Second part is this. Negative is here. This become negative. Okay. So, and then so let me call this I this. Okay, so let's deal with them one by one. Do I have enough space? Okay. This one can cancel. Cancel this. So this thing, AI. this thing equal to dr. So this one is just negative. You can have a negative here, and then change it back into dr. Okay, change it back into dr. Okay, derivative. So you just recall that. Sorry, you just recall that this is just the momentum operator with a constant. Okay, so this is proportional to this momentum operator. Okay, momentum operator. I mean derivative, right? Proportional to momentum operator, right? So this is zero. Why? Because these two has the same parity. It's in a box, right? All the eigenfunction has the parity, right? So this one has an odd parity. It's a vector. It's an odd parity. So you have an odd parity. These two are even the same parity. So this whole thing has an odd parity. Okay. So the only constant with the odd parity is zero. Okay. So this thing is zero. Okay. So let me see this. It looks like I'm missing a G here. I'm missing a G here. Sorry. There should be a G. There should be a G here. Did I miss a G? Yeah. Yeah, that I'm missing a G here. This one should have a G. Because this is only the derivative to get this. And by the chain rule, you have one thing here. Okay, so I'm missing one. So okay, so then this two will cancel. And then this thing will be negative dr. Then this is only these two combined together is just the absolute value square. Okay, and then the QH bar A R, it come out of the integration. Okay, come out of the integration, and this is just one. Okay, so eventually the whole thing just equal to the whole thing just equal to negative QH AR. Okay, just like that. Okay, so now let's go back to get this Berry curvature. Okay, sorry, it's going slow. So the Berry curvature will be I cross this thing, and dA. Okay. And then you can move all this constant outside. And negative, I mean negative I QH QH. So this is a R. Okay, this is a R. And this is just B. Okay, this is just the B. Okay, so this whole thing will be IQ. I'm missing an I somewhere. I see. There's an I here. There's an I here. Okay, because this thing become I derivative G. Okay, there's an I here. There's an I here. I'm missing this I all the way. Okay, so let's take an I. Take an I. Take an I. Take an I. Okay. And then this negative I, so they cancel each other. So there's nothing here. Okay, so eventually you get this whole thing is just a flux. Okay, just a flux. So eventually you get the flux. Okay, so this is the Berry phase. Okay, so yeah, sorry for this long derivation. The result eventually is very simple. It's very simple. So this result is the same as what we got when we don't use the Berry phase. Okay, previously, okay, so it's a kind of a long lecture. Let's review what we have done. Okay, let's review what we have done. So first, we consider solving this Schrodinger equation, okay, for a particle moving in a loop. Okay, moving in a loop. Then we find that the magnetic field will have some effect on the energy, okay? And then when the potential is non-zero, it will affect the solution, okay? So eventually we get the solution. We get the solution. Here, okay, here is the solution, and the flux is inside. It will affect it, okay? So this is just one example that magnetic field will affect it. Then if you want to do it more generally, if you do a more general case, there's a way to solve this equation, even though you are not considering a circular loop. You just solve a general one. All you need to do is in the region when B is 0, you can change the form of the equation into this way. Okay, into this way. And then after that, you plug this inside, you'll find that this is just the solution when you set the A to be 0. Okay, when you set the A to be 0. And then this one is a certain like a integration over arbitrary line. And this point can be set arbitrary. Okay, this point can be set arbitrary. Okay, after that, then you apply this to the previous case. All you need to do is to set a box to confine the particle inside the box. And everything related to the box is contained in this potential. Okay, it's contained in this potential. And then in order to solve this equation, all you need to do is to use our previous technique. That is to set the function in this form. And then this will be the solution when you don't have the magnetic field. This will be the solution when you don't have the magnetic field. Okay, now then you just carry this box to go around the loop, one round to go back to itself, then it will pick up a phase. And that is the phase that you'll get in the experiment. And then after you plug it into the formula of the Berry phase, then you'll find that this is the phase you set. So this is the phase that you go one round. If you go one round, you pick up a phase. That is this. Okay. So suppose now you do the experiment. Okay, this is the B field. You do the experiment, you go one round like this, and you go another round like this. So because for this one, it's going in the same direction, right? So you will pick up 1/2. And for the other one, it's going in the opposite direction. Okay, so you will pick up a negative 1/2. Okay, so eventually you have this, and then you have this. So the phase difference will be just this, you just subtract them. And then this will be just the same as the buried phase. Okay, so this buried phase, when you use this experiment to tune the B, if you tune the B, then this phase will change. This phase will change. Then that means when you plot the intensity as a function of B, you are going to see oscillation. Okay, you're going to see oscillation. So this oscillation is a manifestation of the buried phase. So buried phase is something that you can experimentally measure. Okay, and that is one example. So the Aharonov Bohm effect, it was discovered before the notation of buried phase. So when Barry publishes paper, like when Barry have this new concept of buried phase, and then he pointed out that this Aharonov Bohm effect can be considered as a case of buried phase. So it is a geometric phase effect. Okay, so this is just one example to show the buried phase and how we can deal with a complicated question by using a simple notation. And it actually does not depend on the path. You can do the experimental particle and go far away. Eventually, you get the same thing. It doesn't depend on whether it's circular or not circular, because it's a geometric effect. So all those difference in path, they have no effect on the outcome. Okay, so eventually you get this oscillation. Okay, do you have any questions? So the next lecture we will consider the case in solid state physics. Okay, in solid state physics, just briefly mention in solid state physics, when you're in a Brillouin zone, let's say you have a Brillouin zone, X and Y. Let's say you have a piece of graphene. Okay, this is the direct cone. So for every point in the Brillouin zone, you can define a certain Hamiltonian that depend on the K. You solve this Hamiltonian, you get this energy. Then you're going to modulate the K and make the Hamiltonian go one round. And then you will pick up a phase. And that phase turned out to be, you can actually experimentally manifest it. And it turned out to be an important concept in physics. Okay, but those cases will be related to the parameter in the K space. In the K space, this one is very useful for understanding because this is a real space R. This is a real space R. You're really taking the box, go one round in the real space. Okay. When you go to the R space, I think it will be kind of less transparent. So I think if you can first understand this example, then I think at least you have a better understanding of the buried phase before we go into the cases in solid state physics. Okay, do you have any questions? Okay, if no, then we'll end the lecture here.